Binomial probabilities are easy to calculate when you have a small number of trials. But suppose you want to calculate the probability of getting less than 100 tails in 150 flips of a coin. If you want to get less than 100 tails, the events that would qualify for that would be getting no tails in 150 flips, one tail in 150 flips, two tails in 150 flips, and so forth. And you would have to calculate that all the way up to 99. So that means you would let n be 150, probability of success is 50%, probability of failure is 50%, and then literally you need to calculate the binomial probability formula for all the x values that are less than 100 and add them all up. So fortunately, there is a better way to do things, which is to use a normal distribution to approximate a binomial distribution. Now, there is something you have to check first. If n times p, the number of trials times the probability of success, is greater than or equal to 5, and n times q, the number of trials times the probability of failure, is greater than or equal to 5, then the binomial random variable is approximately normally distributed. And then we can take a shortcut. The mean for the population will just be n times p, and the standard deviation will just be the square root of n times p times q. So this makes life a lot easier. Let's check out some examples. Two binomial experiments are listed. We're going to determine whether we can use a normal distribution to approximate the distribution of x, the number of people who reply yes. And then if we can, we're going to find the mean and the standard deviation. If we can't, we will say why. So part A says it's a survey of 8 to 18-year-old heavy media users in the US, and 47% said they get fair or poor grades, namely a C and below. You randomly select 45 8 to 18-year-old heavy media users in the US and ask them whether they get fair or poor grades. So they're going to reply either yes or no, which makes this a binomial probability because there's only two possible outcomes, a success and a failure. So we would want to begin by identifying N, P, and Q. The number of trials is 45. We're selecting 45 students. The probability of them of a success, saying yes, they get fair to poor grades, is 47%, or in other words, 0.47. Q, then, the probability that they fail, that they say no, would be 1 minus 0.47, which gives us 0.53 for Q. So to determine if we can use a normal approximation for this binomial experiment, we're going to check two calculations. We're going to do n times p, which is 45 times 0.47, and we get 21.15. And then we're going to do n times q, and we get 45 times 0.53, which is about 23.85. Since these are both greater than or equal to 5, we can use a normal approximation. And because of that, we can use the formulas. The population mean will be n times p, which of course we've already calculated right up here. So we get 21.15. So on average, 21.15 of the 45 would say they do get fair or poor grades. And the standard deviation, a measure of how spread out the data is from the mean, is found just by taking the square root of n times p times q. And that gives us approximately a standard deviation of 3.35. In Part B, we have a survey of 8 to 18-year-old light media users in the US, and they said 23% of them said they get fair or poor grades. We're going to randomly select 20 of those 8 to 18-year-old light media users in the US and ask them whether they get fair or poor grades. We would begin the same way by identifying our N, P, and Q. We're randomly selecting 20 people this time. The probability that they answer yes, they do get poor grades, is 0.23, 23%. Q is 1 minus 0.23, or in other words, 0.77. Now I need to check the two calculations, N times P and N times Q. N times P turns out to be 4.6. N times Q turns out to be 15.4. So in this case, one of the values is greater than or equal to 5, but not both. So since N times P is not greater than or equal to 5, we can't use a normal distribution to approximate this binomial distribution. And since we can't use those shortcut formulas for the mean and the standard deviation. So that's the first important skill you need, being able to judge whether or not you can use the normal approximation. Now, the major difference between binomial probability distributions and their normal approximations is that a binomial probability distribution is discrete, meaning that I have bars that are centered on particular values. So if we were doing the 150 flips of a coin, I might get 0 heads, I might get 1 head, I might get 2 head, and so forth. And obviously we would have more bars in that instance. And in that binomial probability distribution, you can only take on those discrete values. We're not going to get 1.5 heads when we flip a coin. So when we find the probability of a particular outcome happening, what we're actually calculating is the area of this bar. Remember, the area under the curve gave us the probability. In the case of a binomial distribution, which is discrete, it's just the area of that particular bar that corresponds to your outcome you're interested in. In a normal approximation, we are allowing the variable to take on all possible values. So we're not just limiting ourselves to 0 and 1 and 2, but we're also able to talk about the probabilities of things in between there. Now, because of that, when we use the normal approximation, we have to apply a correction factor. Since the binomial distribution is discrete and can be represented by a probability distribution, when we want to find the probability, we find the area of the corresponding bar. When you're using a continuous normal distribution, okay, that is again continuous and not discrete, to approximate that binomial probability, you need to move half a unit to the left and the right of the midpoint the bar is centered on, the value you're interested in, to include all possible x values in the interval. And we call this making a continuity correction. Here's a table that tells you specifically if you're looking to calculate a binomial probability of getting exactly C successes, or at most C or fewer than C, here's how you would change the probability as a binomial probability to a normal probability when you use your normal approximation. I actually think it's easier, though, to show you some examples to explain why this middle column looks the way that it does. For example, if I wanted to calculate the probability of getting exactly 5, in a discrete probability distribution, there's only one outcome that represents success, which is me getting that value of 5. But when we look at the continuous probability distribution, anything that is bigger than 4.5 and smaller than 5.5 would actually round to 5. So that's why we apply a correction factor, because when I want the probability of getting 5 exactly, I need to consider 4.6, 4.7, 4.8, 4.9, all the things that would round to 5. And similarly, 5.1 rounds to 5 and 5.2 until I get to 5.5. So as a continuous probability, I would say I'm going to find the probability that x is somewhere between 4.5 and 5.5. And going back up here, you can see x equals 5. I take 5 and subtract half a unit on the one end of the probability, take 5 and add half a unit on the other end. So you can treat this middle column like a formula, or you can just think about what would round to that value and then include it. If I want the probability of getting at most 5, that does include the possibility that I get 5 and everything less than 5. In a discrete distribution, getting a 5 would be a success, getting a 4 would be a success, getting a 3, getting a 2, and so forth. In the discrete distribution, we're not allowed to take on values in between these. So in the continuous distribution, I know I want everything from 5 and below, as we saw here. All of these things would satisfy the probability of getting at most 5. But I also want to go a little bit further again, because anything between 5 and 5.5 would round to 5. So my continuous distribution is actually going to look like this. I will calculate the probability of any x value that's less than 5.5. Going up to the top, you can see how with the formula for at most and c being equal to 5, we're told to find the probability, take x and have it be less than your c value, 5, plus half a unit, so 5.5. Fewer than 5. Now, if we want to be fewer than 5, we have to be strictly less than 5. So in the discrete distribution, I no longer am allowed to equal 5 or 6 or 7 or 8. Those are not values that are less than 5. I can be 4 or 3 or 2. In the continuous distribution, I would want to take 4 and below, but I also want to consider anything that could round to equal 4. So once again, I want to think about going beyond 4 to 4.1, 4.2, and so forth, and say anything from 4.5 down is going to satisfy this inequality. So my continuous probability is actually x has to be less than 4.5. You can see that again up in the table, where when c is 5 and you want to be strictly less than that, you take that 5 and subtract half a unit. Couple more to look at. If I want to be at least the value of 5, the outcomes that would be at least means you can be 5 and up. So in the discrete probability distribution, that would be the values 5, 6, 7, 8. In the continuous side, I would want things that are going to round to 5 and up. Well, things that are going to round to 5 start at 4.5 and get larger. So hopefully it makes sense to you that I would need to consider the continuous probability of anything bigger than 4.5. And more than 5, if I want to be more than 5, I'm not allowed to equal 5 anymore. So the only difference between this example and the last one is we take out that possibility of equaling 5 in the discrete distribution. And because we're taking out the possibility that we can equal 5, my continuous distribution should start at 6 as well, but include things that would round to 6. And those begin actually at 5.5. So to calculate this probability, we would actually want to take the probability that x is any number bigger than 5.5. Now you'll notice on the right-hand side here, for the continuous distribution, I don't have equal to lines underneath these numbers. That is because the probability of a continuous random variable is the area under the curve. At an exact value, the area below it is 0. So going back to the picture here. Now remember, when we're using the normal distribution, the area that we calculate, like for any particular z-score, is always the area up to that particular value, right? Well, the trouble is I can talk about wanting to find the probability that x is less than 5, because I would start at the beginning and I would go up to 5, wherever that might be. If I want to talk about the probability that x equals 5, I'm no longer talking about a range of values. I'm only looking at that moment when x equals 5. So there is no area. So in a normal distribution, that probability will always be 0. And that's why we don't worry about being equal to here, because being equal to a value is always just going to contribute a probability of 0 to the total, so we can just disregard it. All right, example 2 says use a continuity correction to convert each binomial probability to a normal distribution probability. So my binomial probability is being given. So for instance, the probability of getting between 270 and 310 successes would just be written this way. I want to convert that to a normal distribution probability. Now, remember what that means, and again, I like to think about it in terms of the number line, is I have 270, I have 310, and getting between those is obviously this portion of the number line, the numbers between 270 and 310. But I also want to consider those things that are going to round to 270. So if 269 is here, anything that's at 269.5 or higher will round to 270, so I need to include those. And then on the other side of 310, I need to consider numbers that will round to 310. So if 311 is out here, anything that is 310.5 or below will round to 310. So my normal probability will be any value from 269.5 up to 310.5. Part B, the probability of getting at least 158 successes. As a binomial probability, that means I want the probability that x is at least 158, meaning bigger than or equal to 158. Now, to convert that to a normal probability, I'm going to think about, again, I like to go to the number line. I'm going to think about where 158 is. Obviously, the numbers bigger than 158 are going to this side, where 159 would be. But I also want to stop and consider, since this is now going to be a continuous distribution, anything from 157.5 up is going to round to 158. So my normal distribution probability should be the probability that x is bigger than 157.5. Now, the other way to do this is to look at what type of binomial probability you're calculating, at least 158 successes. Go back to this chart here, find the row that says at least. Note my C value for this particular case would be 158. And then what's in the Normal probability column gives me my answer. I'm told the normal probability will be the probability that x is bigger than my c value, 158, take away 0.5. And you'll notice you arrive at the same answer. I tend to favor the number line way of doing it just because I don't need to memorize. I can just look at it and think about it, but either one is okay. If I say that I want the probability of getting fewer than 63 successes, then x would have to be absolutely less than 63. What is that as a normal distribution probability? 63 successes. If I want fewer than that, then I'm looking at everything on this side, 62 and below, because I don't want to equal 63. But I need to consider that everything from 62.5 to 62 would round to 62. So therefore, my correct normal probability should be x needs to be less than 62.5. So this is again what we call applying the continuity correction.